the forward-backward algorithm is what we use to do inference in the hidden Markov model. And the forward-backward algorithm is a perfect example of dynamic programming. Dynamic programming. And this is not programming in the sense of writing a computer program. Before even computer programs were around, people used the word programming for optimization. And so dynamic programming was first used for sort of optimization type of problems, but more generally, it can also be used for doing inference. And so there's not very many really fundamentally different algorithmic approaches to efficient exact inference or optimization. And dynamic programming is one of those. It's really a broad class of algorithms. And here we're going to take a look at the forward-backward algorithm as one particular case of dynamic programming. So if you haven't seen dynamic programming before, this is really a perfect example, I think, of dynamic programming to sort of cut your teeth on. So the cool thing is that dynamic programming allows you a way to exactly and efficiently compute some highly non-trivial things. And it's due to Richard Bellman first used dynamic programming, period. So what is the forward-backward algorithm? Let's talk about the forward-backward algorithm. So I wrote down here the graphical model for the hidden Markov model, and typically we'll assume that these x's are observed. That's the typical situation. And we'll assume, so the forward-backward model assumes that we know the distributions, the emission probabilities. I called these, oops, switching colors on me. I called these the emission probabilities before. So we assume that those distributions are known. We'll assume that the transition probability distributions, or the transition matrix, is known. And we'll assume that the initial distribution is known. So assume these are all known. What the forward-backward algorithm does, maybe I'll put it in blue, the forward-backward algorithm computes, so the goal of the forward-backward algorithm is to compute the probability on zk given x. And let me use x, maybe I'll use x1 to n for all of, actually let me just use x. So here for the next few videos, I'm going to use x to denote this sequence, x1 up to xn. So this will be the vector of all the x's. And let me also use a little notation here. I'll use a variable and then subscript I colon j to denote the sequence from xi up to, so maybe to be concrete, xi plus 1, xi plus 2, up to xj. So for example, x here would be x1 to n. So this will be a handy notation to use. Okay, so sorry, that was a little aside. And our goal in the forward-backward algorithm is to compute the probability for the marginal probability on one of these z's given all the x's. Observe those. And it can be broken up into the forward part, the forward algorithm. And in the forward algorithm, we compute the probability of zk, make that a little clearer, zk, the joint distribution on zk and x1 through xk, so I'm using this convention here, for all k from 1 to n. So we're going to compute these joint distributions. So it's the distribution on, say, z3 and x1, 2, and 3. And we're not conditioning here. And then the backward algorithm, we're going to compute. So the forward-backward algorithm breaks up into the forward part and the backward part. And the backward part is compute the joint distribution of xk plus 1 through n, and given, rather, zk for all k from 1 to n. And of course for all the possible values of zk as well. So here, just to make this, just to be clear here, when I write xk plus 1 colon n, I'm using our convention, and it's xk plus 1, xk plus 2, xk plus 3, up to xn. So this is just notation here. So this is our goal in the forward-backward algorithm. We're doing this, and it takes 2 steps: the forward part and the backward part. And so how do these give us? If we can do these, how do these give us this result? Well, the probability of zk given all the x's is proportional to, as a function of zk, it's proportional to the joint distribution on those, zk and x. And we can condition here. We can break up x. X is, remember, this is x1 through xn, into x1, or rather, xk plus 1 through n, given zk. So I'm going to condition on zk and keep this part out, or rather, and I guess I should say, and x1 through k. So I'm going to condition on zk and x1 through k times the probability of zk and x1 through k. So we can always do this. And now let's look at this. So let's look at this part here. xk plus 1 through n given zk and x1 through k. So I claim that. So let's look at the diagram here. Let's say k is I don't know, k is 2, say. So I claim that this is conditionally independent of this given this. So let's take a look at why that's the case. So xk plus 1, so that would be, xk plus 1 would be all of these guys here, right? If k was 2, if k was 2, xk plus 1 would be all of those. Zk would be this guy, and these are x1 through xk. And I claim, so let's check this. So let's uncondition these. Oh my gosh, what happened? I guess I made that too dark. Okay, so we're going to condition on, I guess I can't uncondition those. Imagine that these we have unconditioned on these x's, and we're going to condition, maybe I'll use a slightly different color for conditioning. We're going to condition on zk. So I claim that these are conditionally independent of these given this guy. So if I condition on this guy, and maybe I'll use like green or something, some dark green for, or it's not really green, some dark green for conditioning now. If I condition on this guy, so let's think about what the d-separation property tells us. So for these to be if these were d-separated with, given this guy, then they would be conditionally independent. So are they d-separated? Well, for them to be d-separated, every path from here to here needs to be blocked. And so is every path from here to here blocked? Well, let's see. So this is a tail here. This is a tail here. And so since this guy is conditioned on, these are blocked at the tails, and so every path, right? I mean, every path would of course have to go through here, and those are all blocked. So yes, so they are deseparated, and therefore these are conditionally independent of these given z2. So therefore, we can get rid of this part. Therefore, this just becomes this. Maybe I'll clean this up a little bit. Cut. Paste. Boom. So that becomes that. Okay, well that's nice. But what is that? Does that help? Well, yes, right. That's exactly, this is the backward part here, right? This is the backward part. And this is the forward part. So by multiplying these together, we get something which is proportional to what we wanted. And since this is just over a finite set, it's easy to normalize. We can just sum over that finite set, get the normalizing constant, and we can get this distribution. So the key part, the key thing to getting this posterior distribution on the z's given the x's is doing these forward and backward steps. And once you have your hands on these guys, it turns out that you can do pretty much whatever you want. Pretty much arbitrary inference. Let me give you a couple examples just to illustrate what you can do. So once you have that, what you can do you can do pretty much arbitrary inference. For example, you could compute the probability of that zk is not equal to zk plus 1 for any given k. So sort of like change detection. One type of thing. Another example would be, well, I'll just give you that one example. I think you can probably see. So this is one example of inference, and there's tons of other things. I mean, pretty much anything, that you want to compute about the z's given the x's, you can do. You can estimate the parameters of your HMM. And by the parameters, of course, I just mean these guys, right? The transition probabilities, the T matrix, the transition matrix, the emission probabilities. If the emission probabilities are, you choose some parameterized distributions, maybe they're Gaussian, so you would need to estimate the mean and variance for the Gaussians for each zk. And usually you don't have to estimate. Usually the initial distribution doesn't really matter too much, but you might want to estimate that also, I guess. And so you can estimate those parameters. And this is done using the Baum-Welch algorithm, which couples the forward-backward algorithm with expectation maximization. So we haven't talked about what expectation maximization is, but we'll talk about that a little later. Another cool thing you can do after you've completed the forward-backward algorithm is you can sample from the posterior distribution on the z's. So you can sample z's given x's. So this would be useful for like visualizing if you had some data, like maybe you had some data, like maybe the handwritten digits or something, or handwritten letters, the writing when I wrote hidden Markov model, and you wanted to sample from possible interpretations of that. You could draw some samples, and rather than just getting like a single sample or something, you could do that. You can get the most likely example. That's called the Viterbi algorithm. We'll talk about that later. But you could also just sort of see what some likely samples are. So those are some applications of what you can do with this. And next we'll take a look at how to do this, how to compute these using the forward algorithm and the backward algorithm.